So today we start a topic which is extremely deep and far-reaching. So I really ask you to use all your brain abilities or your capabilities, because it is really a key point. And moreover, for most people, it is probably new. So you really have to learn it from the very beginning. And so the name I can give to this chapter is Local Approximation. And I have to stress the fact that it is local approximation of a function with polynomials. Okay, so in other words, this is the theory by Taylor Maclaurin. So we already have some examples in these directions, and the first example I can give you is that we all know that the function sine of x is approximated by the polynomial x up to some higher order infinitesimal, little o of x. Of course, for x going to 0. So this is a very harmless expression we know very well, we already used several times, but I want to start reading it in a different way. First, sine of x is the function to be approximated. And x, in this case, is the, let me use this space here, is the polynomial of degree 1 that approximates the function and I recall you that this is the best polynomial. The best. So let me write here. This is the best polynomial of degree 1 that approximates the function. Why is it the best? Because when introducing the notion of derivative, we define the derivative as the coefficient of the best linear approximation to the function, and the only one that allows for a rest, for a remainder, which is little o. Okay, so this is why black. This is why the polynomial. And let me give a name to this polynomial. For instance, P1 of x is the best among first order, first degree polynomial. Of course, if we introduce little o, we have to state clearly in which region of the line we are considering the function. So x goes to 0 here clarifies that the approximation is local. Why? P1 approximates the function, in this case sine of x, only locally. So the message is the following. The very definition of derivative, nothing more than that, provides a first degree, or first order if you want, approximation which is local to a differentiable function. Moreover, if you want to have a pictorial representation, here we have x, which is in this case the first order polynomial that approximates, and the function sine of x is this one. Okay? I don't like so much this graph of the sine, so let me be a bit more precise. So these are the axes, and then it must be quite close to the function because it is the tangent, and here passes here. Okay, not very good. That's a picture, but you understood. So now the question is whether is it possible to provide an approximation to function. So let me say another local again. I want to stress the word local. It is very important, because there is also a theory for global approximation, but it is much more advanced. You will never see it properly. So the question is it possible to provide another local approximation with higher degree polynomials? And the answer is yes, of course, provided that the function is regular enough. We will see that, but for now, let me just give you an example that you know very well. The example is about cosine this time, because we already wrote this equality. The cosine of x is equal to 1 minus x squared over 2 plus Lied law of x squared, again for x going to 0. And notice that here we have a second degree approximation. Second degree approximating polynomial. And in this case, we will call it P2 of x. So P2 of x, we refer this expression P2 of x not only to the polynomial of the cosine, okay, but whenever we have to approximate a function. So P2 of x, of course, depends on the function to be approximated. But this is just to clarify what is the spirit of this topic. Okay, this is good. And so let me let me now try to give you again a picture of the situation here. So the cosine is this, and P2 of x, 1 minus x2 squared over 2, is this. Okay, so and the idea is that here, near 0, the contact between the two curves, between the two graphs, is extremely good. Okay, there is a higher order contact. And now again, I will not prove it. I can invite you to do that. I don't know whether it is easy or difficult, but perhaps it is easy. Yeah, of course. Of course, it is very easy. So here, and this establish that the polynomial P2 of x, which in this case is 1 minus x squared over 2, is the best, again, the best second degree polynomial that approximates the cosine the function cosine of x near the origin. Prove it. Remember that we proved for the first order approximation, like in this case here, that when you use the derivative as a coefficient here, this is the best first order approximation. Now, with a similar argument, a very similar argument, you can prove that this is the best second degree polynomial, so the best parabola that approximates the cosine in a neighborhood of 0. Okay? Now, the other question is, so is it possible to go farther and introduce higher degree polynomials to provide better approximations again locally in the local sense to functions. And again, the answer is yes. And let us discuss this answer on. Let us discuss this answer on a concrete example. The example is again that of the sine. So you have here the function to be approximated is sine of x. You know that sine of x is equal to x plus little o of x as x goes to 0. In other words, x minus sine of x is a little o of x. X goes to 0. So So now pay attention to what I am about to say. I want to say that finding a polynomial, a higher degree polynomial that approximates well the sign, means investigating the structure of this little O of x. So we aim at investigating the details of little O of x. And in particular, the problem is to compute the principal part of the infinitesimal x minus sine of x with respect to the sample phi of x equal to x as x goes to 0. In order to do that, we proceed in the usual way. So first we compute the limit the limit for x going to 0 of x minus sine of x divided by x to the power alpha for alpha larger than 0. Okay? Now, with usual techniques, we know that basically we are not able to do that. But now we have the L'Hopital. And de L'Hopital applies very well here because it is an indeterminacy of the type 0 over 0. So start differentiating and see whether the ratio between the derivatives of the numerator and of the denominator has a finite limit, or in general has a limit. So first, consider x minus sine of x prime divided by x alpha prime derivative. This is 1 minus cosine of x divided by alpha x alpha minus 1. And so here we know exactly what happens because f alpha is smaller than 1, not larger than 1, then this goes to 0. Sorry, larger than. The limit is 0, so we cannot find the principal part. And on the other hand, if alpha is larger than 1, then again an indeterminacy of the case 0 over 0. So let us go to use de L'Hopital again. 1 minus cosine of x prime divided by alpha x to the power alpha minus 2. This is equal to sine of x, alpha x to alpha minus 1 prime, and here it was wrong, alpha minus 1 prime. And again, here we have alpha times alpha minus 1 x alpha minus 2. So, and again, for alpha between 0 and 2. This goes to 0, so no principal part. And again, if alpha larger than 2, then again indeterminate form. Then we differentiate again. So sine of x prime divided by alpha minus 1, x to the power alpha minus 2 prime. We end up with cosine of x at numerator, and here alpha minus 1, alpha minus 2 times x to the power alpha minus 3. And here we obtain something interesting, because cosine doesn't go to 0 here. So this goes to 1, so we cannot fall into another indeterminacy. And here we have the result of the limit. This goes to 0 if alpha is less than 3. This goes to, for alpha equal to 3, 1 over 3. 3 minus 1, 3 minus 2, equal to 1/6 for alpha equal to 3. And then plus infinity when x goes to 0 from the right, and minus infinity when x goes to 0 from the left for alpha larger than 3. Okay? So what we found at the end is that, in particular, so alpha equal to 3 is the order of the infinitesimal x minus sine of x with respect to the sample phi of x is equal to x. Okay? And now we start from sine of x prime divided by 6 tends to 1/6. And here we apply the first theorem of the L'Hopital. So we have that the primitive 1 minus cosine of x where we came from divided by 6 times x goes to 1/6. Then again by the L'Hopital, but this time number 2, we have x minus sine of x prime divided by 3x squared goes to 1/6. So I'm going back through a chain of the L'Hopital, I'm going back to the previous limits. And again, by the L'Hopital 2, we end up by saying that x minus sine of x divided by x to the cube tends to 1/6. Okay? Therefore, x minus sine of x is equal to x cubed over 6 plus little o of x cubed as x goes to 0. And rearranging terms in a more convenient way, we find that sine of x is equal to x minus 1/6 x to the cube plus little o of x to the cube for x goes to 0. And here we have a third order approximation. We call it P3 of x. This is a third degree polynomial that locally approximates sine of x near x equal to 0. And the fact that the rest here is Lie law of x3, this means that P3 is the best third degree polynomial. Okay? So this is extremely important to stress. And again, you can try to prove it, and if you understood how to do this, is really simple. I want to tell you something about this limit that I computed in this way. I was a bit pedantic, but so I stress it by a remark. So I was a bit pedantic in computing the limit. For x going to 0 of x minus sine of x divided by x to the alpha, because I wanted to show how to get the result by an iterated de L'Hopital procedure. In order to prepare you to Taylor formula, to the proof of Taylor formula. Psychologically, to prepare psychologically to the proof of Taylor formula. Then it might be done in a very faster way. So when you have x minus sine of x divided x to the alpha, and you compute the prime derivative here, then you have 1 minus cosine of x divided alpha x to the power alpha minus 1. You immediately know that it is only for alpha equal to 3 that you have this goes to 1/2 times 1/3, which is equal to 1/6, by other method that you already know. Okay, so it is much faster. Then here you don't have directly that for smaller alpha it goes to 0, and for larger alpha to plus or minus infinity, but it is immediately done once you have this result here. So don't get scared by the fact that here I used many times the L'Hopital. Okay, this is all for what concerns the motivation, and yeah, I will use this discussion in order to introduce Taylor formula in the next video.